Got it. So can you see it now?
Yes.
Okay, great. So so first I would like to thank you, Carmen and Yang and Hannah for inviting me to give this talk in MAST meeting. So I will talk about the performance of a scheme on some correlated materials or open shell D and F electron compounds, and try to discuss the origins, the error origins in this correlated materials from density functional theory perspective. So two major errors in a DFT calculations is, one is self-interaction error. I think we have a very good understanding of that. And another one is strong correlation. I think it's still up on debate. I think there are still many things we are not so sure. But what I would like to say is that if we use density functional theory to calculate properties of materials, I think, or we would like to develop something for correlated material, develop density functional for materials. Probably the first step is to crack this self-interaction error first, and then we can get to the strong correlation, or have a better understanding of strong correlation from DFT's perspective. Now, so here's the examples. I think probably many of you understand this and probably understand these materials better than I do. So these are the challenges presented by late 3D transition metal monoxides, for example, manganese oxide, nickel oxide, iron oxide, and then cobalt oxide. So experimentally, right? So you can find the band gaps for the magnetically long-range magnetically ordered antiferromagnetic phase, but when you heat the materials up across this Curie temperature to reach this paramagnetic phase, the band gap remains. So now in the DFT calculations, so usually you cannot open gap if you set the system to be non-magnetic. And I would like to say that non-magnetic and paramagnetic are not the same, but usually people use this non-magnetic in DFT modeling for paramagnetic. I mean, the major difference is the local magnetic moments. So then, but if you let the do the calculations in the antiferromagnetic phase, so meaning that you set up this long-range magnetic ordering at the beginning, so then the popular Purdue-Berg-Enzhoff GGA still has difficulty in opening the gaps. Consistently, I use this table to illustrate that. So you see that PBE with this antiferromagnetic setting in the ferromagnetic, in the iron oxide and then cobalt oxide, so they still predict these two compounds to have zero band gap. Now, if you add this Hubbard U, right? So the on-site Coulomb repulsion to correct this PBE calculations, then you can find that the band gap can be opened. And also, if you take a look at the magnetic moment, right? So PBE significantly underestimate the magnetic moment of this transition metal monoxides. But when you add U, then the magnetic moment is significantly improved. So now there's of course this is so there's Hubbard U in condensed matter physics. It's well defined and understood, right? So this is a measure of correlation in the Hubbard model. So measures on-site electron Coulombic repulsion, and usually is believed missing from single determinant approaches, including the Kohn-Sham density functional theory. So, but in DFT, we also have view this Hubbard U in a different way. So we say that it is a way to create self-interaction errors. So basically, we know that for integer numbers, or for a system with integer number of electrons, so then you can so in exact DFT, right? So they can define these points, but when you allow the electron numbers to be fractional, so then the energy as a function of the electron number should be piecewise segment connecting these integer number points. But in semi-local or popular density functional approximations, usually this derivative discontinuity at this integer number is missing and the curve is smooth, all right? And then this error can be shown as this blue one, right? Then in DFT plus U, then you can have this plus, in the usual implementation, right? So you can add this correction, and then this correction U is positive, and then this correction will penalize fractional occupation, right? So this is just a measure of occupation numbers in the d orbitals, and any fractional occupation will give you a positive number here, and then therefore raise up the energy, all right? And therefore you push this black curve energy to the red correct or the exact one. So therefore the total energy. So in this way we view this Hubbard U to be a way to correct self-interaction errors. Now, then we will have the question, right, from that table I just showed for the PBE's performance on the band gap prediction. So does U add the strong correlation of on-site d electrons to PBE, or is U a self-interaction correction to PBE? So now we would like to answer this sort of in this scans performance in correlated materials without U, right? So now let me just step back a little bit to talk about this scan density functional approximation. It stands for strongly constrained and properly known. So it is a non-empirical and physically justified density functional, and overall improves over PBE with not so comparable efficiency. So the scaling is still the same, and the computational cost is about 3 to 4 times more when you have a very, very large system. So now, scan predicts accurate geometries and energies for diversely bonded molecules and solids, including those with the van der Waals bonds. So now this is the performance of scan on this band gap predictions of transition metal monoxides and without U. So we can say that scan opens the gap for all of them, all right, in this AFM order as well as this paramagnetic phase. And in the paramagnetic phase, we use this supercell-based special quasi-London structure. So it is kind of the spin disorder in this system and to mimic the paramagnetic phase. So then we can say all the gaps are opened, including this iron oxide, which is very difficult. So now this is some results, right? So so this is AFM PBE and AFM scan. So now the band gap for FEO and COO is small, but we have it. Of course, we're not saying that the scan captures all of them, and there's still some residual errors because it's still a semi-local approximation. It cannot get everything right, especially for band gaps. So another thing I would like to point out is this non-magnetic phase or non-magnetic order. So if you do the scan calculation and compare to this AFM scan, so then you can see that the total energy of the non-magnetic phase is about 1.5 electron volts or 0.5 electron volts for all these compounds per atom. So this is a large energy difference. So it's just energetically irrelevant for the experimental observations. So we think that when we try to study these compounds, non-magnetic phase should not be used as a starting point. You should go with this paramagnetic phase. So you see that the paramagnetic phase, the total energy is only like several times milli-electron volts above this AFM. So it's more reasonable. So now, some of the other more challenging cases, this is a metal insulator transition in cuprates with doping. So now, the system we choose is this lanthanum cuprate and under doping by replacing this lanthanum atom, so this green atom here, replace it with yellow strontium. This is called delta doping. Now then, this octahedrals are this Cu or octahedral Cu is in the center. Now the problem with DFT previous density functionals is that experimentally we found that antiferromagnetic phase, so the pristine one is antiferromagnetic and insulating, but when you dope it, so then it becomes metallic. But LSDA and PBE predict the pristine one to be metal. It's qualitatively wrong. And then we found that the scan actually opens the gap, all right? So I will show in the next slide, then also scan predict this metal insulator transition and doping correct. And many other properties quantitatively accurate. So now in this, there are more results. So this is band structures for the pristine scan calculations. So you can see that the band gap is open under the doping, then it becomes a metal. So then this is a magnetic structure with spin orbital coupling. So then scan predicts the spin direction. I think line up in this A direction, okay, and it's consistent with experimental finding, and then also scan predict the magnetic moment is around 0.5, consistent with experimental data, and the magnetic coupling between two copper ions. So then it's very close to the experimental results. It's about minus 130 millielectron volts, and the band gap is also close to the experiment. So these are results that we have. I mean, we published in these two papers. If you are interested in, then you can take a look at them. Here, these are the some of the studies we have for this YBCO7. So this is a nearly optimally doped cuprates. So you can have the pristine YBCO6 then by remove the oxygen atom in this chain, this CuO chain. Okay, remove all of them. This oxygen here, this oxygen here, this is called the chain, and then that is pristine. And then when you put more oxygen in the chain, then you actually suck the electrons in this copper oxygen plane, and then therefore hold up this plane. Now, if you study the, focus on this copper oxygen plane, then you can have this kind of a stripe phases. So basically you have this pattern of copper magnetic moments. Follows the stripe along this is a B direction, and in the A direction you can have some kind of phase boundary. So like antiphase boundary between two domains. So then you can, by doing that, you can model many different stripe phases. And we found that a scan can predict a lot of stripe phases, and then these stripe phases have very their total energies are very close, and then this means this stripe and some for example the AFM magnetic phase, they are competing to each other. So this is kind of a strong correlation that we can capture. Revealing this magnetic fluctuations in this cuprates. So this is published in this PNAS paper. If you are interested in, then you can take a look at that. So now these are some kind of a success story that we have for scans. But here mainly I would like to as a density functional theory development. So I'm more interested in figuring out why SCAM improves over PBE and LSDA over on these correlated materials, especially why can SCAM open the band gaps of this AFM and paramagnetic phase of correlated materials. So here there are just to make it complete. So I just use one slide to lay down this most fundamental equations for density function theory. So in density function theory, of course, we can write down the total energy as a function now of the electron density, right, which can be written as a sum of the kinetic energy or single particle kinetic energy, and then the heart rate energy, and then the internal potential interacting with electron density, right? So and then the exchange correlation energy functional. So the single particle kinetic energy can be written as a summation of these orbital kinetic energies, Kongshan orbital kinetic energies of occupied orbitals, right? And then this phi I are Kongshan orbitals. And the electron density, of course, are the sum of the orbital electron densities of the occupied orbitals. And then the Hutch energy is just a classical Coulomb interaction between electrons. So then there's all the TSU, and then there's the last term in the total energy, right? This VEXT, they are all known, okay? Can be written out as an explicit functional of the orbitals. But the exchange correlation energy functional is the only unknown that needs to be approximated. The way we approximate it is, so this is kind of the John-Purdue's approach. So following to the exact constraints on this exchange correlation energy functional, these are mathematical properties, for example, limits, scaling relations, equalities, and bounds. So then by doing that, it has much good chance to be more transferable between different materials. So then if you have the exact exchange correlation energy functional, then this theorem is exact for the ground state energy and electron density. And of course, if you have better exchange correlation energy functional, then you should have better predictions of ground state properties. So now there's so in the first half I talked a lot about the band gaps, right? So previously we saw that the band gap can not be predicted with this orbital Kongshan band gap. Here the band gap means the fundamental band gap that can be defined as this total energy difference. So second order total energy difference with respect to electron numbers. But recently our work shows that within this generalized Kongshan DFT, where the potential, the effective potential is not multiplicative, it's instead some explicit and continuous potential operators. Then we proved for solids that the generalized Kongshan orbital band gap, the first one here, the left, in the left, so is equal to the fundamental band gap defined by this total energy differences. So that means if you have better density functional for total energies, then you are supposed to get better band gaps, okay, from just a single point generalized Kongshan calculations using this orbital band gap. All right, so SCAM works in generalized Kongshan DFT, and SCAM is more accurate in total energy for a lot of testings than PBE overall. So this is actually very basic arguments I would like to make for the better prediction of band gaps that I showed earlier. So now here since in the talk, the title I said this is about self-interaction error and strong correlation, right? I would like to use so simple example or prototypical systems to illustrate the self-interaction error. So now first one is this self-interaction error by this H2 plus, right? H2 plus only has one electron, right? So then you should not expect electron-electron correlation or electron-electron interaction. And Hartree-Fock method is exact for one electron system. So then this Hartree-Fock calculation or binding energy curve. So H2 plus, you can stretch this H2 plus. So basically move one proton away from the other and then calculate the electronic energies with the Hartree-Fock, then it should be exact. And then you have this reference curve. And then you can also do this DFT calculations, for example, PBE. You can see at equilibrium, right? So then PBE is not so bad. But the error develops huge because here this error is in EV, right? Electron volts per atom. And then it is about -1 or 1 electron volts per atom. So this is huge. So then you can also do scan, right? At equilibrium, yeah, it's improved a little bit with over PBE, but it also develops significant errors when the bond length is large. But it still improves over PBE, right? Noticeably. So then that means this scan and PBE both have self-interaction error, but scan is likely having a smaller self-interaction error. I will talk about the consequence later. So now there is a strong correlation, right? Usually we use this H2 to illustrate, right? The ground state of the hydrogen molecule is spin singulate because you have 2 electrons and then the total spin should be 0. And then the electrons strongly correlated at the dissociation limit, meaning that 1 electron you will put, is forced to be on 1 proton. And because it's spin singulate, so then if the electron is spin down in the left, so then the spin of the other electron will be spin up in the other proton. Therefore, they are strongly correlated in terms of the spin configuration. Now, DFT, if you enforce this spin singulate, then it will give you significant error. I mean, like this Hartree-Fock, right? So then this is a restricted scan. So they start red line. So at large R, right? So the dissociation limit. But if you allow the spin symmetry breaking, meaning that you only sample one of the spin configuration of the spin singulate, so spin down at the left and spin up in the right. So then you only sample this spin configuration, it's spin contaminated. But you can still write out the spin wave function for that as single slit determinant. And then you do the calculation, and then you will find that although the spin, the solution is not the eigen function of the spin operator, so total spin operator, but the total energy is very accurate, all right? So this is the unrestricted scheme calculation for this H2. So good total energy. I mean, if you connect to the earlier slide I showed in the relation between the total energy and the band gaps, this meaning that if the system has spin symmetry breaking, so in nature or artificially, so then your band gap predictions should be much improved, right, if you allow spin symmetry breaking. So now, here is the consequence of self-interaction reduction and symmetry breaking in open shell D and F electron systems. So this self-interaction error reduction from PBE to SCAM usually means that the electrons are less delocalized, right? So so the self-interaction error has this kind of effects in the electron density. It will, because of the self-Coulomb repulsion is much stronger in this case than the exchange correlation component, and then this self-Coulomb repulsion then have the tendency to push the electrons away. So then this makes the electrons more delocalized. But if you have a better self-interaction, so I have a better functional that has smaller self-interaction error, then this delocalization error will be smaller. And then with the spin symmetry breaking, real or artificial, then this spin symmetry breaking can help total energy descriptions. So both this SIE reduction and spin symmetry breaking has this importance of stabilizing this local magnetic moments. So this is what we say from when you compare SCAN with PBE and LSDA for some transition metal and f-electron oxides, all right? So then usually you can see that the magnetic moments from SCAN is much better than from PBE and LSDA. So this is the electron localization we can see. So we just take the electron density difference of SCAN and PBE, right? So then that means this blue regions here is negative and red is positive, meaning that SCAN actually moves some electrons in this bonding region. So this is oxygen, right? And then this is manganese, and then moves some electrons in the interstitial, in the bonding or interstitial region around to the manganese side, right? So then that means you localize the electrons around these transition metals, and therefore stabilize more the magnetic moments. And then this is gives you better total energy descriptions and the band gaps. So here we also started one more system, this f-electron systems, SMB6. So there are many debates on the system, and we actually published an interesting paper in this PRB and talk about this scheme that actually solved those challenges within one single framework. We found this very interesting, and so if you are interested in that, you probably can go to take a look at it. But here, what I would like to show is that the density states from a scheme in comparison with the experiment and this DMFT and the PBE, right? So the middle one, so this panel C is scheme with AFM and scheme with this SQSPM, right? So the paramagnetic phase modeled by this special quasi-random structure. So you can see, right, of course, this PBE, so all the density of states just clustering around this Fermi level, which is quite wrong. Now, SCAN, right? So it has, I think, qualitatively captured the feature and even comparable to this DMFT results. So it's quite encouraging. It seems to suggest that self-interaction error here is more important, and maybe SCAN should be the starting point for these correlated methods. Now also I show this electron density difference between scan and PBE, and you see the same localization, okay? And then the anisotropy of this electron density around this Samarian atom. Scan just can give you this anisotropic description, or more anisotropic electron density than PBE. So here it's a little bit photon dispersion of nickel oxide. So this is totally in the total energy calculations, right? So because photon, this is based on the harmonic approximation, and then what you want to get is just the this dynamic matrix, which is total energy as a second order derivatives of total energy with respect to the displacement of the atoms. And then this actually can be decomposed into three terms. So the nuclear, this is nuclear energy, all right? And then they say the electron's response, electron density response to the displacement of the atoms. And then this is the second order of this external potential generated by this nuclei. So then you can say that LDA and PBE gives you two soft. Okay, so there's blue dotted line, right? LSDA, and PBE there's red line. So it's too soft for the optical branches, but this R2 scan is just a revised version of scan for better numerical stability that I mentioned earlier. So then it's quite good in comparison with LDA and PBE. So, and we know that this is mainly because, I mean, this is right, the good photon dispersion by the right reason, we believe, because LDA usually can give you good photon dispersion for some normal materials, for example, silicon, but that is by error cancellation. But by that, what I mean is that LDA usually gives you two small lattice constants, and then this term is overestimated. But usually LDA is too soft for the electron density, and the response is too large. And then because this sign is negative and this sign is this blue term sign is positive, then there will be error cancellation. Now R2 scan actually usually gives you quite good lattice constants, so then it will give you quite accurate description for this blue term, and then also quite a good description for this response of the electrons to the atomic displacement. But the key here is still the self-interaction error. So the magnetic moment is more accurate from R2 scan than this LDA and PBE for the nickel atom. This kind of my conclusion. So scan improves over PBE significantly for the electronic, magnetic, vibrational properties of transition metal and rare earth metal compounds. Scan predicts competing magnetic and charge stripes of cuprates, implying these magnetic fluctuations. So this is kind of the strong correlations between electrons. And then we show that the scan has smaller self-interaction errors than in PBE, meaning that implying less delocalization errors and stabilize magnetic moments and open band gaps. So I expect that the scan can serve as a better starting point for many-body techniques because it has less errors to be corrected. So this is just some kind of hope that I have now. So now, but because scan is still a semi-local approximation, as I showed in this H2 plus, right? It still have a has a significant error when you stretch the H2 bond. So in that case, in those cases, right, stretch bond situation, so non-local density functionals, for example, local hybrid, so produce longer self-interaction correction, or this Fermi-Loftin orbital self-interaction correction, or the localized local orbital scaling correction by Whitehouse-Yan's group, and many others that solve self-interaction error are designed for solving the strong correlation problems with many-body techniques. So what I mean is that probably we should, I mean, if we want to use density functionals as a starting point, so then probably we also need to pay attention on this self-interaction error first. But of course, there are probably some like efficient method like plus U that we can use when this non-local density functionals are not available. So this is kind of, and I would like to acknowledge my funding agency, DOE's computational and theoretical chemistry program and synthesis processing science program and the NSF CREA program. Thank you. Okay. Thanks.
Thank you. I'll just stop recording.
Okay, thanks.